Hello friends, welcome you all to the 26th session of home-based development. So in this discussion we will be covering whatever is left over, some more on the cache memory organization. Some of the desired elements which we have not touched upon so far in detail, I will do that in this lecture, and then we will specifically see how cache is controlled in a inside an ARM system. Okay. So I mentioned that some design elements need to be covered, right? What are the design elements? Suppose you are designing a cache, what all different parameters we have to tweak to come up with a final design. Okay. So there are so many input configurations possible. Based on that we design the cache, and then we get a final design of cache, and which we will be integrating with the processor. Okay, in our case it's the ARM processor, and then we will be integrating it with the ARM. Sorry about this. Okay, and then later on this will also be connected to the memory controller, or it could be memory maybe inside, or it will be outside. So we will be designing a cache. Okay, there are so many ways we can design it, and so what are the design elements? We will be covering it in this class, as well as I will tell you how do we control it. Okay, suppose, okay, let me little bit maybe when I come to the coprocessor I will talk about that. So that will give you how we control the cache inside a processor. Okay, so that's going to be our focus. So with this discussion we will be completing the cache related discussion, and then we will continue with the virtual memory management from next lecture onwards. Okay. Okay, what is the block replacement? Okay, if you all remember the basic cache design, let me again give you some introduction as a kind of a reminder. So based on the size you will know that which is the main memory and which is cache. Okay. So processor is somewhere here. Okay. Our processor ARM is here. Now let us assume, okay, this main memory and this cache size. Okay, this is of 16 words. Okay, just for discussion sake. Okay, so this is 16 words are there in this. Okay, one word is 4 bytes. Okay, okay. Now this is also we have 16 words. Assume that we know that each cache is storing it in blocks. So we are assuming each block is of size 4 bytes. Okay, let me write it as a capital B so that you know that it is not a bit, it is byte. So 4 bytes of block, that is we consider 4 byte as one word, and then we are designing, we have a system. Okay, it's not practical to have only 16 words of cache, but just for discussion purpose. Okay, so how many blocks are there? 0 to 15 blocks are there. Okay, and then let us assume there are 4 such 16 words. Okay, each one of them are 16 words. Okay, so how many totally? 32. This 16, 32, then this 64. So 64 words, or 64 into 4 bytes of main memory. Okay, only this much is there. Now each of these 16 words each can be divided into words, right? Each of them are, all of them are accessed in terms of words. So let me give you different blocks color. Okay, this is one block. not one block. This size is equivalent to the cache size. Okay, the whole thing is equivalent to the size of the cache. Now what are we trying to do? We have a main memory which is 4 times bigger than the cache. Okay, naturally main memory will be more than that, so it is 4 times bigger than the cache. Now we are trying to see how it can be mapped. So just to refresh on yesterday's class, last session, let me tell you how this is done. Okay, now one thing I showed you, direct mapping. That means what? Whatever. So this first block word here, word is a block. So first block of that memory is mapped to this. Okay, first block. Similarly, the first block of this is mapped to the same location. So once the main memory is there and your cache is there, what do? You divide this main memory into the equal size of the cache. Okay, if suppose 16 words are there, you divide it into 16 words. So it should be a multiple. Okay, first of all, the main memory should be multiple of the cache size. Okay, first point done. Then once you do that, then you can have the same number of blocks in each of those sessions. I will call it as maybe a session, one session. Okay, so each session will have the same number of blocks that are there in the cache. Now direct mapping does, what does it do? It just maps every block into the same location. So that means this first block will be mapped to the first block of this, and this first block will be mapped to this first block of. So now if we are talking about a replacement policy. Okay, why do we need replacement? Because we have a limited cache memory, and then once we are done with this, and then we want to get a new block from the memory, we want to place. We want to see where we can place it. So in the case of direct mapping, when we are doing a direct mapping, what happens? That the location where each block in the main memory is supposed to come and fit in the cache is already fixed. If it is lying in the first one, it will come to the first location. Now if it is in the second location of the session, it will come to the second block of the cache. So it is one-to-one mapping, but multiple sessions are mapped to this one cache. So how do you decide the replacement? Suppose you want to get a new block from here, which happens to be a third block in this. Do you have any freedom to choose any other block other than the third block? You cannot, because the mapping is done through hardware. Okay, please remember, it is not done at the like a software programmable. Some things are done, but once you decide the mapping, it is going to be fixed for the particular execution. So this is going to be the mapping. So you don't have any choice other than removing the block which is already there in this location. Okay, if it happens to be different, only you are trying to bring this. Or if earlier also this same block was sitting in the cache, you won't be considering it as a cache miss, and you won't come to the main memory. But when there is miss, that means other than this block, some other block, either this this or the third block here is in the cache. One of them may be in the cache. So we have to evict this, put it back into main memory, and then bring a new block into this location. So the location where we are getting this block is already predefined based on which block you want to bring it into the cache. This is the case for direct mapping. Okay, let us for in the same place I will explain you the other mappings also. Okay, now let us see if it is going to be some other thing. Okay, let me take a different color. Now suppose if it is a okay, let me erase this mapping. Okay, fully associative. Suppose if you consider it as a fully associative, okay, that means what? Any block in the cache, in the main memory, can come and occupy any place in the cache. Assume that the design is the same. Okay, 16 blocks are there, and then here also the same 64 into 64 blocks are here. Okay, in the main memory. So this is organized in such a way that we can bring any block in the main memory to any location in the cache. That means you can pick anything here to evict it and then bring it here, bring the new block here. it doesn't matter, it is not tied to a particular location. That's what is fully associative. Okay, so you know that it is now we maintain the remaining address of that main memory in the tag as a tag, and then locate which location of which main memory block is in the cache. So we will search through the tag and then find out. So that is fully associative. What about set associative? It is another method of mapping the cache. So assume that I am adding one more of the same 16 words. Okay, 0 to 15. I have added one more here. That means it is 2 set associative. Okay, 2 set. If it is 4 set associative, what I would have done? I would have added 4 more, 2 more. That means totally there will be 4. Then it will be equivalent to how many you have in the main memory. There is no point in this case having a 4 set associative for this kind of a main memory. Correct? So if it is 2 set associative, it is actually we have a half the size of the main memory here in the cache. So in this case, what happens? Either this suppose you are talking about the first block, any one of this first block can be in one of these 2 locations. Okay, so in this case what happens, if suppose we are saying that okay, we are trying to get this block, but this block and this block are occupying this first locations of the cache. Now you have to decide, after coming to that particular cache line or a block, we have to evict one of these 2. Okay, then it is choosing between 2 of the blocks which one to be evicted. So that is the replacement policy. So in case of set associative, we have a restricted set or restricted blocks to consider, but it is better than the previous one. It is not that only we identify only one block and that needs to be evicted. Now we can choose one of them, whichever is being used more often we can retain it, and the other one we can choose to evict. So we are talking about, based on the different mappings, the replacement algorithm will change. That's what I try to explain here. Okay, I hope this is clear to you. It's a recap of what we discussed in the last class. So let us go forward. So no alternatives in case of direct mapping. I told you in direct mapping what happens, the particular block which needs to be brought into the cache exactly comes to a particular location in the cache. So we don't have any choice other than everything that earlier already occupying in the cache, whatever is there in the block, that needs to be thrown out. Okay, thrown out in the sense it should be written back to main memory. In two-way associative, the option is to choose one of the entries. I told you. Okay, so suppose we have 2 set associative, means two entries like this. Suppose this block is coming, equivalently the same block in one of this can be chosen. Okay, we have an option here. So what is the advantage of having an option? Okay, let me explain. See, when you have an option to choose, okay, you can place the block which is coming from main memory into one of the places in the cache. That's what I am saying in two-way associative. Okay, two-way. There are two-way set associative. Here I can choose either this or this. So what is the advantage? See, we can add some more attributes to each block in the cache, okay, to maintain the accesses. Suppose you see, how do you decide a block is to be maintained in the cache or not? Okay, it is based on the usage pattern. Who decides the usage pattern? The program which is being executed by the processor. So based on the program sequence, and whether it is a data or whether instruction, doesn't matter, whether it is a loop or it depends on the control flow of the program, and then what is being executed. Based on that, we might have some more hits happening, okay, to a block, okay, in the cache. So what I mean by a block in the cache, see, when you have a two-way set associative, there are two different parts of the main memory is in the cache. Okay, let me change the color to say, see, assume that this is mapping to this, so it is sitting here. and then another. Okay, let me choose a different color so that you find some difference here. So another block is here. Okay, it could be a data or instruction, doesn't matter. Okay, let us for a for a simplicity, for our discussion sake, we let us assume that this is some data D1 and D2, and based on the color, maybe this is D2 and this is D1 is in the cache. Now, based on the program sequence, either D1 may be accessed more often or D2. We don't know. Assuming that I showed more arrows here, so assuming that D2 is used more often, that means in the program for loop there is a variable I which has been mapped to some register R2, and then that R2 happens to be in this block. The variable I happens to be in this block, and which has come here and sitting in the processor, and that I is moved into the register inside R2, and then we are doing an operation called inc R2, increment R2, then we are doing some move R1 to R2, and then there is a add R2, so many instructions which are all of them are using the same right R2, which happens to be a variable I that is actually being used in the for loop. So what happens, the ARM processor will be trying to get that value I, maybe whenever it is written into, then it is right into the cache, whenever it is to be read, it is read from the cache. So there are so many read and write are happening. Okay, so 1 second. So sorry. So what happens? This is being used more often compared to this. That's what I'm trying to say. This variable was accessed sometime back, and then the program is not using it. Now there is another variable coming which also happens to be mapped to the same location. Now let me change the color. So this is the variable or some value which has to be mapped to this location now, because up to this point direct mapping, after that it is set associated, it can be chosen, either you can sit here or here. Now if suppose in the cache controller, okay, along with every block, if you are maintaining a counter, okay, counter, it's a hardware counter, so every time it is being accessed, this particular block is accessed, it is incremented, okay, and then similarly there is a counter for this entry, so that is also getting incremented. But because this has, since it came into the cache, okay, it is the incrementing happens for every new block coming into the cache, it will be reset to 0, and then it will start incrementing from there until a new block comes and occupies the location. So now what happens? This will have a more count, maybe 10. This is having some 3, assume. Now when this has to be brought in, it is very easy to choose. Okay, this should not be removed, so we choose this. That means the hardware decides that okay, this particular block needs to be evicted. Now when it has to be evicted, it has to do some more things. Okay, if it is a data, maybe it would have been modified, then it should be written back into the same location. The value should be written back into the same location, and then this new value will come into this place. So this won't be disturbed. Okay, so now what happens? This count will become 0 now because new entry has come, and then whenever it is being accessed, it will start incrementing. So this is what happens in a processor inside. So you should know when we read something like this, what it actually means. Now you should go back to the program level, and then how it is converted, related to the register level, and how it is impacting the accesses to the cache. Okay, and then choosing this. So if you have all this in your background or back of your mind, then you will have a better understanding. So two-way associative, the option is to choose one of the entries. In fully associative, I told you any block in the cache can be picked. Okay, it is not that only a particular block in main memory is mapped to one location. It is mapped to anything, any to any. So in that case, what happens? You can do the same thing, but you have a wider option. See, earlier in set associative, if it is two-way set associative, you have a very narrow option, either this or this. Okay, whereas in fully set associative, if you are maintaining the same counter like this, every block is maintaining a count. You can choose the least count and then throw that block into the main memory and then get this new block from there into that location. So it is easy. You have a wider choice. Okay, always we want to have a wider choice in anything in our life as well as in our hardware architecture. So this is one advantage of having a fully associative mapping. Now, what are the different algorithms? Okay, I mentioned algorithms here. So there are so many algorithms which can be implemented in hardware. Please remember, it is not that one exception will happen, one software handler will come and then it will execute this algorithm in a program. No, it is not in software. Please, we always associate the algorithm means it is tied to some software and we write an algorithm in the software. This is implemented in hardware. Okay, so we cannot have a cache replacement policy in software. Okay, we are bringing cache only to make it faster, and then we say that we want to execute this algorithm in in a software and then come back and then decide, oh okay, I am choosing this block, please evict it. By the time so many instructions, even this executing this handler will involve cache. Please remember, even executing this cache needs cache. So these things cannot be implemented in software. It's all in hardware. This I am bringing it to a point because you should have it in mind why it is not possible. That is very important to know. So what is FIFO? So a simple algorithm. Okay, whichever, suppose it is, well, let us for a discussion sake, let us assume that it is a fully associative. Okay, this choice. Please remember, the algorithm has to be different way, it has to be done for different mapping. Okay, a cache is designed with multiple parameters. I told you. One of them is how it is mapped, whether we have chosen one of this algorithm. After that, within that we want to check, we look at a replacement algorithm. So our set, the number of entries that we are looking at to find out the best suitable block to remove depends on the mapping. So, in our case, I am assuming that fully associative means we have all the blocks in the cache to be a candidate for replacement. In that case, how do we decide? We can choose FIFO. That means what? The block which came first. Okay, in terms of time. Okay, FIFO means first in first out. So the first block which has come among the blocks which are there in the cache. Please remember, in terms of time. That means what? We have to have some count on how many clock cycles have elapsed, or maybe how many multiple clock cycles. It depends on how many bits we are maintaining for each block. So there should be some hardware maintained to keep track of time when a particular block has come. So it is not the absolute time; it may be some relative measurement. So it is based on the block which has come very early will be evicted. So what is the logic behind it? It is a temporal locality. Okay. In terms of time, suppose this is some data entry which has been used maybe time 0. Okay. Now 50 millisecond has elapsed. Okay, nanosecond or okay, millisecond is 2. Okay, 500 nanoseconds have elapsed. Okay, so many instructions have been executed, and then we tend to, based on this temporal locality, we tend to believe the data or the instructions which have been used most recently will be used in the future too. Okay, that is the temporal locality. So based on this logic, the instruction or a data which was used long time back in terms of time may not be used in the near future. So if we choose a block which was brought into the cache so late in terms of time scale, it is not likely to be used in the near future. So if I take it back and then fill it with a new block, I am not going to encounter a miss looking for this block again immediately. This is only an assumption. Please remember, it is not, nobody has wrote it in a check and then or a agreement has been signed that this block will never be used in the near future if it was used long time back. No, nobody is giving you any assurance. But this is the best probability. It's all works on probability. So most probably this is not going to be used compared to the blocks which have been used very recently. So this, if I use this algorithm, then I am going to gain benefit based on this. Okay. So again, whether it is going to be used or not, or whether this is going to be used, see, you may choose a block based on this logic, but if there is a possibility that that block is used immediately after that, then what will you do? You may have to bring that block again back into the cache. So it is a investment, time investment, and a wastage of cycles. So we are trying to optimize it based on the behavior of the software. Okay. So this is one thing. Now what is random? Don't give any association, just pick up one of the blocks in a random sequence. So there may be a random seed. Okay. Any random generator in a software, you might have seen some software libraries, generating random numbers. The random numbers are very much used for so many algorithms, in a software world. Okay. For encryption, or even to decide about where where to choose, where to save some key generation. Those things are all based on random algorithm. So the randomness is also decided based on some hardware interface. Okay. So maybe a temperature variation in the chip, or the fluctuation in the clock. There are so many hardware logic is used to bring in a random phenomena and then generate a some count, maybe a 32-bit, or maybe random bits means more bits if you keep, it is a more safe. So maybe 128 bits. Some things are maintained inside the hardware, and then it generates a random pattern. So if you have such things, maybe you can choose the bottom portion of the random number and then decide which was which are the blocks to be chosen. I am talking about fully associative, so you are having a freedom to choose one of the blocks. So we choose one of them and then decide to evict that. So that is one way of deciding a block to evict. Another one is recently used. That means you are maintaining a count of, this is similar to what I told you. So if it is not used, the counter would have been less. Okay. If it was used recently, the count would have been more. Okay. So based on the again, usage is one thing. Okay. Another one is whether it was recently used or not. That is suppose I maintain a time stamp of when a particular block in a cache was accessed. Okay. I keep updating that sequentially for all the blocks. I'll say that okay, this was used, is actually time sensitive. Okay, it was used in terms of time, whether it was used or not. No, we are ordering the block in terms of usage pattern, and then we choose the one which was not used for quite some time. So it is the same as well as what I told you just now. So the cache controller tracks references to all the blocks and computation proceeds, and then increase the track counters when hit or miss occurs. So if there is a miss, then we are trying to choose a particular block. If it is a hit, we don't even run the replacement algorithm. The replacement algorithm is required only when there is a miss for a particular data and needs to be brought into the cache. Now, when we want to bring into the cache from main memory, we are trying to choose one of the blocks to be evicted. Okay. I hope the whole sequence is understood by all of you. Very good. Now, we are done with the replacement. Now write policy. Okay, let me we are not. I intentionally did not talk about this because I know that I am going to be covering this in this section. So see, we were maintaining on bit, valid bit was there, and then a dirty bit. Okay, for each of the block. Please remember all these attributes maintained, the counter or the tag. Okay, any attribute maintained for the cache entries are all at the block level. Okay, at a block level, it could be 32 bytes or 64 bytes, anything, any amount. Okay, at a block level, these are maintained because why we cannot maintain it at within that, because we are bringing a block whenever we want to get into the cache, and then we replace the whole block whenever we write back. Okay. So now what is write policy? Okay. Now for us, for our understanding of this write policy, let us assume that it is a data cache. What we are talking about now, the processor, okay, is accessing the cache element. It has come already in the cache, so it is reading it. It may do two things. It may read an entry from here, or it may write into the okay. Maybe I should write right here. It may write a particular element into the cache, or it may read from the cache. So okay. Now when we are writing into the cache, okay, what happens? This element, data element, it could be a byte or a word or a part of the block is written. Okay, the similar location is there in the main memory. Agree? Inclusion, right? Because this data, whatever was here only, was brought into the cache, and then later on it saw a hit, and then it was trying to access from here, and then writing into also it is writing into this location. Now what happens? Assume that before this particular data element was brought into the cache, the value was 10 in this location. Okay, let me change the color again. Okay, the value was 10 here, and then the 10 was read by the processor. The 10 came into the processor. How did it come? It was doing a LDR. Okay, LDR it was doing R1 comma some address in R2. That address that R2 was pointing was here. So we brought the whole like Hanuman, we brought the whole block from the main memory into the cache, though it wanted only a word. Okay, so now what happens? That 10 also came into this cache, and then the 10 was moved into R1. Now 10 is sitting in R1 now. Okay, now assume that the processor is executing a add instruction. Okay, R1 comma R2 comma R3. Okay, sorry, again R1 R4. Okay, yeah, sorry about that. Let me erase it. Okay, so R1. What am I trying to do? I am adding R1 with R4. Assume that R4 is here inside the processor. If you are having some value 5, we have added R4 with R1 and written into the R1. That means 10 is added with 5 and then 15 is written into it after this execution. So what happened? This has become 10 now. Sorry, 15 now. Okay. Now assume there is another instruction. I am writing it here. Okay. STR. Okay. STR R1 comma R2. Assume that R2 is not modified, so it is still pointing at the same location, and then we are trying to write this value, that is R1, whatever is there, into R1 into R, the location pointed by R2. Now do you think that it will go to main memory? It will not, because it is already having it here. So what happens actually is, okay, this location, okay, gets written with a value 15. It is not doing a memory write. Then what is the use of having a cache? So 15 is written into cache for doing a STR, okay, instruction, storing this value into memory. But as far as the programmer is concerned, we have saved it in the memory, okay, but actually it has not gone to the memory yet. It is in the cache. Now we have an option. Who has an option? The processor has an option now, okay, whether to write this immediately or not. Okay, there are so many write policies possible. Not so many. Okay, 3. I am going to explain you 3. Maybe the latest research may have more, but what is implemented in ARM and what are some popularly available write policies are 3 of them. That means you can decide to say, I will not write this until this block is going to be replaced because some other block needs to be brought into the cache. Now I will decide, okay, dirty bit will be set. Okay, please remember dirty bit is actually what? This location has become dirty. Okay, actually what is main made? What we brought is modified now. What we have brought from the main memory is modified. No longer it is same. So it has become dirty. Now when we are evicting this block, that's what I am saying. Evicting means we are trying to get a new block into the same location. It may be because of any memory mapping algorithm. Doesn't matter. We have chosen this block to be evicted. Now, if the dirty bit is set to maintain the consistency that the originally programmer wanted this to be written into the main memory, so we have to oblige the programmer's intent. So the processor needs to do what it should do. It should write back this value into that location before bringing a new contents from another location into the cache. Okay, it is a temporary storage. Remember that. So it has to be written back so that 15 comes here. Okay. Now, if we delay the writing, yes, what I am saying is true. But suppose I may have another algorithm to say that I will not delay, I will write it immediately. You may wonder what is the use of cache. Maybe reading I may get a benefit because I will get it from cache. But whenever I write, because normally reading is more often done than writing. Okay, into the memory, assuming that is the kind of a program flow, and that's what is a normal control flow is. So we can get the benefit of cache by reading it from cache more often. But whenever we do a write into the cache, it is also written to the main memory. That is one way of deciding. Another one is I wait till the block needs to be evicted. Until then, I will keep writing into the cache, but I won't bother to update the main memory. But I will write it only when I need to remove it from this cache. So that time I will write. That is a delayed writing. Okay, that is one way of doing it. Another third way is a write buffer. I will talk about the write buffer later. Okay, subsequently. So these are the three things. I hope you understood the background of this. Okay, why we are talking about the write policy and where it fits in. I think this will make it clear to you. Now we can go a little faster. So when a new data is written into the cache, there are three options to choose from regarding the writing the same into main memory. So when we say write into the cache means, is it written into the cache from main memory or written into the cache from processor? Good question, right? Which write are we talking about? Data is written into cache. It is not this, it is this. When we are writing into the cache from the processor, okay. So it is now what has become? It has become dirty. The dirty bit is set, and we have a choice: either write through, or write back, or write buffer. Just defer. Okay, these are all three names. Don't worry about what they understand, what they mean. I will just explain you now. Before that, I will ask you one more question. Does instruction cache need to implement this feature? Will there be a need to write into instruction memory by the program? So what I am saying is, suppose you have a cache which happens to be instruction cache. You will bring instructions from the main memory, right? Is there a need for you to write into the instruction cache by the program? Program is writing into the program code memory. See, a program itself a code is writing into a code base, another code area. Okay, there are some possibilities. Okay, one is it may be to a memory transfer, or maybe a program may find a new content to be written into a program memory. So this there are some the self-configurable processes are there where the processor configures itself by changing the program. Okay, self-configurable processor. Or another example I could tell you is interrupt vector. The interrupt vector, let me tell you. You remember that interrupt vector I hope. Okay, location from 0 0 to from 18 to 4 locations, 32 locations. Okay, so what happens? We are writing the branch to the handler. Okay, this is a reset handler. There are handlers for data abort, instruction abort, all those things. So now somebody has to write into this location for the processor to access it when the exception happens. Okay, so before that somebody has to write, and this happens to be in the instruction space of the memory. So this part of the addresses will be mapped to the instruction cache. So they will be sitting in the instruction cache. So we may have to write into these locations also at some during the bring up, board bring up, or initial reset locations, reset stages. So yes, very occasionally. One example is the write into the interrupt content. So this is just nothing to do with the write policies. Okay, this is another question I am asking you, whether instruction cache also needs to implement this policy or not. But mostly it is meant for data cache. Okay, please remember the policies that we decide for a cache may not be same. In a same processor, I may have an instruction cache and then a data cache, and then I may have a policy to say that this is there is no write policy, or maybe whenever I have an instruction cache, I may do a write through policy, and then for a data cache, I may have a write back policy. So we can decide different policies. I may have a block size of 32 bytes here, okay, and then I may have a block size of 64 bytes here in the data cache. So we will treat the instruction or data cache in a different way if it happens to be a split cache. But suppose we have a separate cache for both instruction and data. But if it is a unified cache, then the policies will be uniform across the cache. So these things you should have in mind. I'm just explaining it whenever I am getting an opportunity. So let us see what these three mean. Okay, write policy. Write through means always write to memory and cache simultaneously. So when we write into the cache, when the processor writes into the cache, it also writes into the main memory. Okay, assuming that the writes are less frequent than reads, then we gain some slices out of having a cache. But write through policy does it immediately into the main memory, also it gets reflected. Okay, so writing into memory is 100 times slower than cache, which is some approximate number. If there is a frequent write, okay, it impacts the performance because of the increased bus size. That is very natural, right? If you have a very frequent write into the data, then we will have a performance impact. Otherwise, there is a gain. Okay, more reads are done than more compared to write. I hope this is clear to you. Write policy, write through policy. Another one is write or copy back. Okay, some in literature the books may refer it as a copy back or write back. So both are same. Write only into cache, but just a dirty bit in block where write was performed. It writes only into the cache. Okay, not into the main memory. So for a moment, the value here will be different from the location actually it corresponds to. Okay, where it was brought from the main memory. This will be different from this value. Okay, but we write into this only. We don't do the processor doesn't write into the main memory. When a block with a dirty bit is on, has to be replaced. Please remember, replacement, we are trying to bring another block which maps to the same location in the cache, and we need to now edit this particular block which was corrupted. That means if the dirty bit is set, now we have to write back into the main memory. So it is a delayed write. So this is efficient when there are frequent writes into frequent writes. That means what? The program which is running in the processor is writing into the data more often. Please remember, it is not modifying any register or something. It is actually STR or STM is being executed more often. Store is done more often by the program. Because of that, the memory cycles are created, but it is actually writing into the cache only. So it doesn't go to the main memory. So we are saving a lot of space, a lot of time, because memory is not impacted at all. In the sense, it is not accessed at all. So this data will be different from what is written into this. But when it is to be evicted, that time we will take care of updating the memory. But do you see any issue here? I will show you. I will give you an example where we will have an issue. If this will happen only when there are multiple processors exist in the system. So this is one processor. Okay, P. It is P. Assume there is another processor in the same system. Okay, when I have in the SOC when we have multiple processors, okay, the cache may be same. Okay, again there is a design decision whether to use the same cache or different cache, that is different. But even if it has a different cache, there are that is not an issue. Okay, let us assume in our case there is a P1 and there is a C1 and there is a C2, cache 2 for this P2. There are two processors, but they are having the same memory. Okay, they are working on the same main memory in the same space. So now what happens? There is a possibility that a data element which is being accessed from this main memory and which is residing in the cache 1, that means the cache belonging to the processor P1 is acquired by this guy. P2 also wants the same location, same memory content. It wants to read it. Now what happens? If this guy has already updated it and this value is no longer reflecting the current situation of the data, but this processor wants it now. So there is a coherency problem. This is what is called cache coherency, because two different caches are there for different processors working on the same memory space, and a memory content is already taken to the cache and then this guy is updating it locally. Now when the other processor wants the same content to be copied, it is having a stale data. This is called stale data in the cache, sorry, in the main memory. No longer the data in the main memory is valid. So this is a separate topic. I may need another hour to explain this. So there are cache coherency policies, MSI. Okay, there are different policies are used. So that is not our part of the discussion in our class. So we will not talk about it. So what I am saying is, whenever such multiple processors are accessing it, then this policy is a bad choice. Or if you have a choice of this, maybe we need to implement some cache coherency protocol to handle it. Otherwise, write through is a better one. Okay, in the sense it will be immediately reflected in the main memory. So if this guy wants the data, it is already updated, so it can get the latest updated data from the main memory. So it is write through is a write through doesn't need a cache coherency policy. Otherwise we need a cache coherency protocol to be implemented. Fine, don't bother about that. Understand that there is a problem when there are multiple processes. Need to take care of cache coherence when multiple processes share the data. Please remember, if it is not sharing, no issues. Suppose P1 and P2 are working on a different locations in the main memory, they don't share any data at all, then they will be doing only restricting their accesses only to their own part of the main memory. So please remember, it is main memory, that physical memory needs to be separated. They are accessing different part of the main memory, then we don't need to worry about somebody, this guy P1 accessing it and P2 using it. That kind of situation will not happen. Okay, I hope it is clear to you. Now what is write buffer? I mentioned this write buffer when we discuss about logical physical cache. Let us see. Writing into the cache also writes into the write buffer. So let me draw a diagram now. Okay, and because this is blue, let me change the color. Okay, cache. This is processor, this is cache, this is main memory. Always I am just you don't get confused with what is what. Now assume that it is a data cache. Now something coming in between. Okay, who is coming? So color is not so different, but okay. Write buffer. This is the inside the processor. Okay, assume this is inside the SOC. The boundary is very much required. So whenever any data is written into the block, okay, in a block, please remember, in a block multiple words are there, n words are there. This write buffer can be a few words. Okay, it may not be block size. So let us assume that the width of the write buffer is one word. Okay, in that case, let us assume that it is a FIFO. That means what? The latest, it is like whatever data is written into is coming here, and then it goes out to main memory like this. Okay, so up to this point is filled, and these are all empty. Okay, some few more entries. Maybe 4 entries are here, and then some 12 entries are here, which are free. So write buffer is a hardware, okay, intermediate buffer. Whenever a processor does a write into the particular location, there may be a word, it gets written into the write buffer also. Okay, both places, here as well as here. Now what happens? After that, the processor continues with its execution. Okay, so what was written into the write buffer, unless we maintain, okay, the both the data as well as the address of the data write, it has to be there both. Okay, because we might return a a location which belongs to this location, A1 address A1, and then A2 maybe some data is written, and then some location A3 address 3 is written. So this D1, D2, D3, okay, these are all data actually written into this. What is supposed to have been should go there is written into this now, but it is reflected here in 3 locations in the cache. It is reflected. Unless we maintain this A1, A2, A3 also along with the write buffer entries, the write buffer cannot go and write into the proper location. It has to know which location it has to write into, because writing by this written by the processor at time t, okay, t1, then at time t2, maybe later in the time, if this is flushed into the main memory. So write buffer does it at a different time, at different point in time. Okay, so it has to have maintained the address also of what is being written. So once it is written, then the write buffer can steal some time, okay, from the memory cycle is free, then it can background, it can keep pumping all these fellows out to the data, right, memory. That is what happens in a real processor, and our ARM processor also supports this. So the depth of how many words in the write buffer is design dependent, particular implementation dependent, but the processor supports that. I hope this is clear to you. I am giving all the examples so that you know exactly what is happening. Okay, so the data comes from here, just written into the cache, and then the data bit also may be set, because it has to indicate that it is changed. Okay, but it is not bothering about the write policy is chosen as write buffer. Okay, so it also writes into the write buffer. Now let me tell you one scenario where the write buffer is not getting any memory cycle at all to pump these values into the main memory. When will it happen? When the program is also getting access from the same bus, so program is getting access, or maybe new memory cycle is happening, okay, or coprocessor is in the process, in the system is accessing the main memory so often, or the DMA is doing something. So there are so many the external factors which may impact how the memory is being used by different guys in the system. So okay, please remember the coprocessor is inside, okay, the SoC. So what happens is the write buffer is not getting time to write into the main memory. So in that case, what happens? The complete write buffer is filled. Okay, it looks very clumsy. So let me erase everything. So that you get a better view. So write buffer, I am drawing only the write buffer. Okay, is filled with lots of values, a data value and an address value. Okay, this is D15 and then A15. Okay, in the FIFO order, so it is supposed to go to the main memory like this, and the processor is writing into this location like this. Now this is all full. Now the write policy for the processor is, whenever you do any write into the cache, make sure that you write into the write buffer also. Now what happens? It is full now, full. Okay. Now the processor is doing a write. It gets written into the data cache, comes here and then sees that the write buffer is full. Now what happens? It would have been because of some store operation, right? Store instruction getting executed by the processor. Now what happens? This is in the execution stage of the pipeline. Okay, please remember our old friend pipeline is still there. It is getting executed here. Now the processor needs to decide whether to throw this out of the execution side, no, stage and then move the decode stage instruction which is there next to the execution stage. Now what happens? Since the write buffer is full, the processor decides to stall this, stall, pipeline stall. Because if this policy is followed, this is what will happen. So the instruction will wait. Okay, the processor stalls means it will now no longer issue any. Naturally, see here, you see the side effect. The processor stalls. Because of that, there is no pre-fetching of instruction. Correct? So if pre-fetching doesn't happen, the instruction access is not happening from the main memory. Correct? In that case, what happens? The write buffer will get some cycle to write into the main memory. So these are all kind of chain together. Chain reaction happens. If you have to have all this in your back of your mind. Okay, what happens? As a system designer or as a programmer or as a hardware designer, you should know if something happens in the processor. When I say pipeline starts, what is the side effect of that? There is no prefetch happening. If there is no prefetch happening, what is the advantage? There is no memory access meant for instruction is happening. It is not reading the instructions from the main memory. Then what happens? The write buffer gets some few memory cycles. Memory is not busy, so it will write into the main memory. So it will flush this out. Then there will be one space created. It's a FIFO order. So what happens? This whatever was written here will go into this location, the last location, and this D2 will become D1. Then it will move into the pipeline like a FIFO. Then what happens? This instruction moves out of this. Once it is written into the write buffer, processor assumes that it is written into the main memory, and then it takes the next instruction. So this is what happens. Okay. I hope this is clear to you. Let us see. Write into the cache, write into the write buffer. The memory controller takes care of writing it from the buffer into the main memory. So later on, it is later in the sense whenever it gets time. Write buffer efficiency depends on the ratio of write to the number of instructions executed. What does it mean? Number of times the STR kind of instructions are executed. Okay, if it is suppose 1 out of maybe 10 or maybe 20 or whatever, no number. That means there are not too many STR instructions in the stream. In that case, you will get a benefit because the processor is not going to write into the write buffer so frequently. Then the write buffer is likely to get a free memory cycle to flush it. Okay, from the write buffer. So we are gaining from this particular policy. The processor gains. As a system designer, we gain. Very good. Let us see. The data written into write buffer is not available for reading until it has executed the write buffer. So what I mean by that? See, there is a possibility that when the particular data is sitting in the data buffer, write buffer, okay, this is a data cache. Okay, an element is here. Okay, this is modified and it is sitting here because it was modified. It was a policy write buffer policy, so it is here to be written. It is not in the top of the queue, so some more data need to be written. Then only this will be written. Okay, now what it says is the data written in the write buffer is not available for reading until it has exceeded the write buffer. So the reason being, I tell you, the possibility you may see that okay, if it is in the cache, why can I not read it from here? You have to have it in your back of your mind. The eviction, the replacement policy is a background part. Okay, it is another background thing happening. So there is a possibility of this particular cache entry, okay, is evicted. In the sense, it was actually written into write buffer, okay, when it was in the cache, okay, and then because of the replacement policy, some other data was supposed to come and this is deleted. But this earlier address, it could be here, okay, because it's actually, you remember, write policy is for used for replacement also. So it is written into the buffer. We can now, you don't have to worry about the dirty bit or anything. Okay, we can edit this and bring a new data into this. Okay, assume that the same location, a new data is brought into the cache. Okay, because we are written into the right buffer, processor assumes that okay, I know it will anyway one day it will go into the main memory. Okay, not one day, within few cycles it will go into the main memory. So I don't have to worry about keeping this in the cache. So I can flush it out and then bring a new value here. Now what happens if this is not gone into that? We can't. No, there cannot be a read to the same location which is lying here to be brought from the main memory, and then we cannot place it here in another location because it is a fully associative. The same location wherever this is pointing at, okay, this is what is pointing at, this location is here. We can't bring it to the some other location, the stale data, because already there is a very most recent data is available here. This should go out to the main memory, then that should be brought into the cache. So it is not available for read until this is flushed out of the write buffer. So the processor keeps track of, okay, whether particular entry is there in the write buffer, then it doesn't allow the reading to happen. So basically what happens, suppose LDR is happening, okay, from the same location, then this instruction will not proceed. Okay, it will not proceed, it will be blocked till this write buffer flushes it, and then the data is brought from that to the cache to some other location maybe. Now it will proceed further because the data is brought into the register also, wherever it is. It is in the cache as well as in the register, so it can proceed. So that is what happens. Okay, I hope I am explaining more so that you understand the logic behind it. So multiple writes to the same location will leave the lost data written in the location and the other writes are lost. So what I mean by that, one more thing we should remember. Suppose there is a data here, okay, B3, and then address is A3, and whenever a write to that location is happening, okay, in the cache, if it is in the already one entry was there, it has gone into the data bank, write buffer, but it is still not written into the main memory. Then one more write is happening. Suppose processor is writing into the same location again. Now what happens? For the same location, a new data has come. So what it will do? The processor will write that new data here also in the write buffer. Okay. Anyway, it knows that it is in the pipeline to in the FIFO to be written into the main memory, so it will update it. So any intermediate writes are reflected in the write buffer, but it is not reflected in the main memory. Okay. The intermediate write, but the last write will get reflected here. That is what I am saying here. So if I erase it, multiple writes to the same location will leave the lost data written in the location, and the other writes are lost. In the location means in the main memory location. Only the last write will be left in the main location, but intermediate writes are only happening in the write buffer, and it is not happening here. But as far as the correctness is concerned, it is the last data is written, so no issues. Okay. But it will not be any case when multiple processors are there, but I am talking about a single processor, so it is not an issue. It is called write collapsing or combining or merging, write combining or write merging or write collapsing. Okay, so this if you encounter these words, remember that it is what is happening is the data is getting written into the write buffer entry, but it is not getting into the main memory. When it is due for flushing, it comes out with the last data written into that will go to the main memory. I hope this is clear to you. If the buffer is full, the processor has to wait. I explained this scenario just now earlier. Okay, now we are going into unified cache. I told you that instruction and data can occupy the same cache. Okay, in that case, what happens? A particular location, a particular block in the cache can be competing for instruction to be for an instruction to sit or for a data to sit in the location. So both of them are competing for the possible for a same location. Okay, we should is not enough if you know that okay, this is the diagram and this is what happened, but you should know the background, what is actually it means. Okay, see what I when I say that instruction and data competing for the same location in the block, what it means, when your prefetch is happening, that instruction is coming in, sitting in one particular block in the cache. And similarly, when some LDM is happening, loading from memory is happening, that is also coming and sitting in a cache. But both can be mapped to the same location if possible, that they will be competing for the same location. Okay. Now, what happens? Caches for data and instructions are combined. The core and data accesses can affect each other. So when they are competing for the same location in the cache, they can impact each other. Okay. So it is like the code which is actually the code like LDM or STM is also a code. Okay. Actually, an instruction, when you are executing this, when you are accessing this instruction, it is going to create a instruction cache hit or miss. Correct? Because this instruction is accessed in the prefetch stage. And after some 3 cycles, when it enters the execution stage, it is going to create an issue with the data cache, because it is going to create a memory read or memory write. So that is going to cause again a disturbance to the cache. So an instruction which is 3 clocks behind can come and cause a disturbance to the cache. Okay, so they are dependent. So load and store instructions can cause structural hazard because cache is common for. So when what I mean by structural hazard, the blockage is happening, maybe a pipeline is stalled because the particular block is not available, or there is a miss, so it has to be brought from the main memory. So it is a structural hazard. That's what is happening. So the load and store instruction can cause a structural hazard. Okay. Very good. And a split cache doesn't have an issue because they have a separate physical caches, and I told you that it can be different size and different block, and it can be of different write policy. You can do anything, okay, independent of each other. Okay, so you can design this and design this independent of each other based on the requirement of a particular program running in the processor. Okay, so that's what it's a split cache. So cache for data and instructions are separate. Both caches can be configured differently, and they can be accessed in parallel. That is very, very important. They can be accessed in parallel. Okay. One entry in an instruction cache may not, or will not impact the instructions in other cache. Okay, there may be a dependency. Okay, something happening here may have an effect on some mismatch happening here. Okay, there is a side effect may be there, but it is not that one entry here is not as tied to the unified cache case. Okay, the same instruction can try to emit a particular block, but what is happening here will have a side effect here, because if suppose instruction LDM is happening, then there will be a data entry coming here. Okay, that way there is some dependency, but actually the access to the cache of this and this are misses happening here and it's happening here or whatever, they are independent of each other. So they can be accessed in parallel. So when a prefetch is happening, it is going to access from this. See, that is one more important thing you should remember. When I am saying it is in parallel, means the prefetch happening will be making the instruction cache busy, whereas any execution happening here will be keeping the data cache busy. So they can be in parallel. Okay. So that's the advantage of having a split cache. So what are the multiple level caches? There can be number of caches in the system. So in an SOC, we can have, so far I showed you only one cache because we want to explain what are the policies, design elements are associated with the cache. Then once you are now clear with one cache, now I can introduce one more cache. This is level 1 class L2 cache. I am showing it as both are inside the queue. Now size wise I need to show that L2 cache is bigger than L1 cache, and it will be a multiple of this. Suppose this is 8 kilobyte of cache. This can be 16 kilobyte or 50 kilobyte. Okay. and the main memory can be a few hundreds of kilobytes or megabytes. So what happens? Actually, the L1 and L2 cache is the cache for L1. Okay, so just a scenario. Okay, for the processor, L1 is a cache. Similarly, for L1, L2 is a cache. Suppose if the processor tries to find something here, it may encounter a miss. Then it will come and see whether do I have it here, because this is the bigger size, right? So maybe previous success that cache the entry was here and then it is still lying here because it is a bigger thing. The replacement will be more often here compared to L2 cache. So replacement, okay, that means any block going out and getting replaced. So if you don't find it here, you are likely to find it here. Then what happens? It is brought into this immediately, and this is said that okay, I am, this is being used here. So there will be a separate policy for this and separate policy for this. What I mean by that is it can be different, but the kind of size what we decide in the system has to be a multiple of elements. Okay. So what is the advantage we get? If there is a miss here, we can try to see whether it is available here instead of immediately going to the main memory. If it is not in L2 also, then what happens? It is brought from main memory. So when a new block is brought from main memory, what happens is it gets actually bigger block is here. Okay, the sizes of blocks may be different. Okay, the block size may be 32 bytes here. Okay, and 64 bytes here. As I told you, as we go away from the memory, the number of bytes we transport will be bigger. So when we need only 32 bytes, it is a miss here. Okay, it is not available here, and the same location is not available in this. Now what happens? L2 see no longer L1 is communicating with the memory. L2 is communicating with memory because that is closer to the memory. So L2 says I want to 64 bytes of data around this location. Okay, which is aligned to 8 byte or 4 byte whatever. Then that data is wanted to the cache, and part of it, based on what part of the 64 byte is required by this processor may need one word or one byte from here. So based on that, a part of this location is copied into this location and then given to the processor. Okay. So what happens when this processor is accessing the next maybe another location which is closer to 32 bytes? It is not here. This block is not here because only 32 bytes are 32 bytes are available here, whereas the next subsequent value might be here because we brought 64 bytes from here. So when it encounters a miss here, it is likely to find a hit here. So now what happens? It will bring the next set of 32 bytes here, and then maybe it can replace the previous one so that it doesn't have to touch other blocks. So now what happens? We are gaining a hit because of having a L2 cache. So this is the scenario of how L2 cache might save us from going to the main memory more often. Okay. So split caches. So L1 cache can be on chip or L2 cache may be on or off chip. Normally L1 is a split cache. Okay. Whereas L2 cache can be unified or split cache. What I mean by that, the instruction and data, okay, of L1 cache may be different caches. Okay. Whereas L2 cache, bigger cache L2 may be common. Both D1 and L1 will be, this is unified. Okay, and then this is communicating with the main memory. Okay, and processor of course talks to these two bits. Good. I hope you understand. When you see any processor architecture internal diagrams or blocks, you should be able to relate more. So L1 cache always maps the contents in L2. Okay, this is very important. L2 cache size is normally in multiples of L1 cache. I told you that. Okay, that's all. So what are the different design parameters? Now if you see each of the elements, you should have very good clarity and familiarity, and not only familiarity, you should also understand that. You know direct map by now. Okay, set associative and fully associative. I call it a scan because it's a accessing the cache with the full associative mapping is CAM, okay, content based addressing. So content addressable memory, okay, and replacement policy can be round robin or random or LRU. LRU is what? Least recently used. You know the right policy now, okay? Doesn't it look very familiar? And you know about unified or separate caches, and you know about physical cache and virtual cache. Just to refresh your memory, processor is here, and MMU, which I am going to talk in the next class, okay, and MMU memory, main memory is here. Now cache can be here or here. What is this? This is the virtual address and or logical address, and this is the physical address that MMU converts it. So cache can be either here or here. It's not both places, either one of these places. And if it is here, it is logical cache, and if it is here, it's a physical cache. What does it mean? It maps the logical cache, logical addresses to the entries in the cache, whereas this cache maps the physical addresses generated by the MMU to locations in the cache. That's all. Okay. So you understand these two also. So you understand all the entries here. Okay. If you don't, please go back either one lecture in this lecture itself or go back one more lecture. Okay. Now on cache feature, I am not sure whether you will be able to read them all, but you can refer any manual. These are all different word sizes, 8 or 32. Okay, it could be logical or physical location, and the two-way set associative. I told you 2-way, 4-way, 8-way, but there are 32 ways, 64-way processors. No, caches are there. That means what? Directly mapped to the cache, but inside that it could be in one of the locations. Suppose if it is a 64-way cache, it could be one of the 63, 0 to 63, 64 locations in the cache in the particular directly mapped line. It could be found in one of these locations. Okay, so there are different families of processor: ARM 720, ARM 920, strong ARM 11. And then data or NVIDIA, instruction cache. How much of size? 32 kilobyte or 8 kilobyte. There are different sizes. Cache line size, block size, 4 or 8 words. 4 words means 4 into 4 bytes. So 8 words maximum. You can see that only 32 bytes are there. Okay, but later processors will be having that. But it's a block size of or line size of the cache. So you can see that. Kind of different values given to each of the elements. So we have addressed each of them in detail. So you should be an expert in cache now. Okay. Now we have talked about cache inside the processor. Let me just give you some more than 10 minutes. Let me take. Okay. Cache is here. Let us for a moment forget about MMU, which is not in our purview now. Cache is here. Okay. So if there is no MMU, what is the type of cache here? It is physical cache. Okay, because there is no MMU, so whatever address given by the processor is physical address and physical memory. So in this case, I told that the cache can be configured. Configured in the sense I can configure it for write policy. Some things are decided in the hardware, but sometimes what happens is the hardware is configurable. So because when the IP is given of an cache controller, they cannot design one IP for a particular type of a policy. Okay, then it is not an IP, right? So cache controller will have a configurability in it. That means you can choose write through policy, okay, or write back policy. One of the write policies I can choose, okay, or I can choose the memory mapping policy. I can choose one of them. Once you choose a particular set, then it may remain as same throughout the execution of the program. But the choosing a particular configuration is, or you can even you can choose the IP and then have that only limited circuitry in the system so that your SOC is limited. That is fine, but sometimes you may want to give the configurability to the system programmer. In that case, what happens is the configurability is given to the programmer. Okay, I don't know what. Okay, so now what we will do is we will see what all different coprocessors. It is actually configuring the coprocessor. Now cache is done by coprocessor. Why coprocessor? See, cache controller itself is considered to be a coprocessor mapped to this particular ID, coprocessor ID. The reason being, accessing the coprocessor is not a memory cycle. Okay, please remember, it is nothing to do with the memory access. Okay, and they are not so. Whenever you do a memory access only, the cache controller comes into play, comes into play, and then when we are saying that we are configuring a cache, if it is the configurability is also is mapped to the main memory or memory map, if those registers are also memory map similar to peripherals, then we are in trouble because we cannot configure the memory or the cache or the MMU. So MMU also can be needs to be configured. So whenever you want to configure any of them, they can't be in the memory map. That means it can't be in the 2 power 32 locations that can be addressed by the ARM processor. I am talking about only 32 by the processor. So they can't be in that location. So the ARM designers have nicely designed such a way that the controller of cache or the controller of MMU configuring it is mapped to the coprocessor. That means what? We can use those coprocessor instructions that we have seen, MRC, MCR. Okay, only these two. Okay, MRC, MCR is what? Either coprocessor to register, one of the ARM register, or register to coprocessor. So ARM inside a register, some contents can be written, and then it can be written into the cache controller. So you have to assume the cache controller. See, cache is here what we have seen so far. Cache controller is a totally a different element which is associated with the cache. So let me call it as a cache controller. So this is mapped to the coprocessor world. So it is mapped to coprocessor 15. So if a processor throws some instruction with a coprocessor ID 15, and then it conveys some particular location, then what happens? The coprocessor controller gets written, which happens to be a based on the number you choose, it can be a cache controller. Then what happens? Cache gets configured. Then when you do any memory access, it will be accessing the cache. So you may wonder where these MRC and MCR instructions come from. They come from instruction memory. The instruction memory is also in the. So it is nothing. It's not independent of memory because the instructions are sitting in the memory. So they have to be mapped without a cache. So these are all non-cached items. Okay. These some part of the initial memory which is accessed for configuring this cache controller MMU. They are all non-cached. So these instructions are non-cached, so they can be directly accessed. So cache will not be coming into play at all. And then the processor will configure the cache, then it will enable the cache. Okay, that is the flow of things which you will be having a better understanding when I talk about MMU. But in this case, you remember that the caches are also to be configured using coprocessor instructions, and there are 32-bit registers that programmer can write into or read from. Overall system control configuration can be done using them. Cache configuration can be done, and this is all different tightly coupled memory, MMU and NPU. Okay, don't worry about them. I will talk about it later in the subsequent classes. So apart from cache management, where is the cache? The coprocessor 15 is also used for configuring other controllers. So that is not our topic of discussion in this section. So you should know that cache controllers are designed or configured using these coprocessor instructions. So they need to be enabled only when the configuration is done for the cache. Till then, the instructions are accessed from a non-cached part of the memory. So that part of the memory which is holding the instructions for configuring the cache are accessed without the cache getting involved. So ARM can directly access the main memory and then do the job. If you know this, if you can understand this particular background, I am happy. Okay. So we will cover these things later. Now coprocessor 15 register. Please remember these are all the some primary registers. That means if you recall the instruction, if I am calling it as MRC, there is a CPID somewhere here, I think, okay, 8 to 15, if I remember something. So CPID, the coprocessor ID is in the instruction like this, and then there are some operands we talked about, okay, operands which are actually the coprocessor registers, okay, coprocessor COP registers. So what I am talking about primary registers and secondary registers are this OP1, operand 1 and operand 2. So you have a 15-bit main, no sorry, not 15-bit, 4-bit. So 0 to 15. So 16 coprocessor registers can be accessed. So these numbers are varying from 0 to 15. So you can access them using these operands and then mention the CPID as what? 15. With the CPID coprocessor 15 I told you, then we can do different jobs. Okay. So it is all designed and given by the ARM only. These coprocessor controllers are ARM IP, means IP coming from ARM. That is why they have decided that okay, this is the registers I will be using to configure them. So in your SOC, if you have a cache, you will have a cache controller along with that. So you will write these registers and then configure according to the instructions. Okay, what needs to be written into, then the cache will behave that way. Okay, so this is how the configuration of cache happens. Now, what is a flush cache line job? Okay, these are some jobs. Okay, I am explaining clean and flush. I think it is better to understand this. Flushing a cache means suppose you have so many data, so much of data is there in the cache, and then the processor is restarting. Okay, reset is given. Then you can decide to do a flush. Flush in the sense all the entries in the cache are made invalid, and even if there are dirty entries here, they are not written into main memory. Okay, they are not written into main memory. Invalid block without writing back the dirty block into main memory. Okay, if there was a write back policy which was delayed, right? So it was not write through. So but some entries were there which needs to be written in the main memory, but when the processor is restarting, there is no need to write them all, right? So you can, there is one scenario, there may be many scenarios where you don't want to write this data into the main memory. So flush is one control, okay, one command you can give it to the controller cache. Clean cache is another command you can give it to the cache. So these are all required when there are the process context which are happening. Okay, P1 is executing in the processor. Now P2 is coming into the ARM processor. Now whatever was used by the P1 needs to be returned back into the main memory, and then so that P2 can start using the processor and then start using the cache also. So for that you need to clean the cache. So clean the cache means if suppose there are dirty entries in the cache, it should be written back to the main memory. So one command can be given to the cache so that it writes back everything into the main memory. Okay. I'm giving you the scenario. Lockdown in the sense not allowing selected blocks from replacement. See, there is a maybe I will see there is a need for some part of the cache. Okay, some two blocks are there can be locked down. Okay, this is cache can be locked down. It could be instruction cache. The sense suppose you have for FIQ. Okay, FIQ. FIQ vector. The FIQ vector is pointing to some location in the main memory, which is the handler, FIQ handler. It is here in this location. Assume that these instructions are all mapped to this location in the cache, and then you want to say that they should be locked down. What I am telling you is, whenever the ARM processor is executing, okay, it will be using for its own execution, it will be using this instruction cache for its program. Whenever an FIQ happens, okay, interrupt, it may be an external interrupt coming from outside world, then it has to go to the interrupt vector and then access the handler. Suppose if all the instructions meant for FIQ are all in the cache itself, it will not go to main memory, it will get the handler and then everything in the cache itself. So FIQ can be executed, the sense handler can be executed without any delay, because all the instructions meant for handler are all available in the cache. Okay, it will be happening only when the replacement doesn't happen for these blocks. So you can lock down saying that don't even consider any blocks appearing in this cache block to be for replacement. So replacement happens only within these locations, and these locations are not replaced, so it happens. Okay, FAQ can run faster. So that is the purpose of this lockdown. I hope you understood all this. So we covered quite a lot about cache in this, and we may not be talking about cache anymore. And by now I think you have a better understanding of cache, and you can read more literature. Please don't stop with this. Go and read some literature, some books to have better understanding and clarity. Okay, you have to internalize whatever you hear from this. So reading more will help you to streamline your thoughts and understand them better. Okay, I enjoyed really sharing this with you. I hope it was useful. Talk to you in the next class. We will start the next class with the NME, virtual memory. Okay. Thank you very much for your attention. See you in the next class. Have a nice day. Bye bye.